are going to discuss in this lecture about the boundary conditions. In the last lecture, I told you about the general heat conduction equation in Cartesian coordinate system, cylindrical coordinate system, as well as spherical coordinate system. We can reduce those equations as per the requirement of the situation. Depending upon what type of conduction problem is to be solved, we can convert those equations into different forms. We have already seen how we can change these forms of the equation. Now we will try to find out the solution. In order to find out the solution, we need to find out certain physical conditions at the boundaries specifically, and that those conditions are called as boundary conditions. So in this lecture, how these boundary conditions are to be specified, that we are going to learn. We are going to start with some introductory remarks. Then I'll discuss about the boundary conditions like temperature boundary conditions, heat flux boundary condition, convective boundary condition, and radiative boundary condition with some closing remarks. In this temperature boundary condition, heat flux boundary condition, convection and radiation boundary conditions, I am going to tell you how we can write down the mathematical formulation of the condition with the example of a plane wall. Equally, these equations which I am going to write are can be used for cylindrical as well as spherical systems in the same way. So let us start with the introduction. I am Professor Nitin L. Birud. The background of the problem, we have already derived this expression, that is three-dimensional conduction equation for a Cartesian coordinate system with internal heat generation and unsteady situation. Now in this case, only one thing is simplified, and that is the material is assumed to be isotropic, and that's why its conductivity is taken as a constant. It is independent of the direction x, y, and z. And we are getting this equation. We got it in the last lecture also. Now we can reduce this, we can simplify this equation in this fashion. It will become d square t upon dx square is equal to 0. So from the last lecture, you can tell this particular equation is for one dimensional steady state conduction without internal heat generation. So there is no heat generation, unsteady steady conditions are there, and the temperature gradients in y and z directions were also ignored, and we are getting this. And instead of partial differentiation, now it is written in terms of full differentiation because temperature is the function of x alone. So this is a modified form for a given condition. Now in order to find out the solution of this equation, we need to integrate this equation. So if we integrate it, you will get this. The first integration results into a equation dt by dx is equal to c1. C1 is a arbitrary constant of integration. And this equation where we are getting the temperature gradient in terms of some particular term, here it is constant but it may vary depending upon the type of problem. This particular equation is called as temperature gradient equation. Now what is the use of this temperature gradient equation? Once you know the temperature gradient, you can use this temperature gradient in the Fourier's law of conduction to get the required rate of heat transfer at any location from for which the temperature gradient is known to us. So this is where this equation is going to be very handy and very useful. Now again, if you integrate this equation, you will get another linear simplified equation, that is temperature in x direction. Temperature in x direction is equal to C1x, integration of C1 is C1x plus another constant of integration, that is C2. Now you can see that this particular equation is of a straight line, simple equation, that is y is equal to mx plus c. So this temperature distribution in a one dimensional steady state conduction without heat generation in a Cartesian coordinate system is a straight line. This conclusion directly we can draw from this equation. Now this particular equation is called as temperature distribution equation. Now once again I'm going to back to the first equation. This is the general form, reduced form, second equation. Third equation is the temperature gradient equation obtained after the first integration, and the fourth equation is the another integration resulting into temperature distribution equation. Now the next step is to find out the solution. Now by solution I mean to find out the values of these constants C1 and C2. Once you know these values of C1 and C2, you can substitute these values in C1 and C2 in this temperature distribution equation and temperature gradient equation to find out the temperature gradient as well as temperature distribution at any location in the object. So what we need to do for getting this values of C1 and C2? Let us draw a diagram. Now we have got different solutions. Now this particular equation, temperature x is equal to C1x plus C2, can have multiple solutions like this. This values of temperatures at both the ends of this object can satisfy these conditions easily. That's why in order to have a particular solution, a specific solution, we need to give a specified values of the temperatures. So for this specified values of 60 degrees Celsius and say 20 degrees Celsius, you will get some specific values of C1 and C2. And those values of C1 and C2 are only applicable when the temperature of one end is 60 degrees Celsius and temperature at the other end is 20 degrees Celsius. And that solution along with those values of C1 and C2 will become a specific solution for that given boundary condition. That is what we need. So we need basically to specify the boundary condition to obtain the specific solution for that particular boundary condition. So the first task is to find out the or write down the mathematical expression for the boundary conditions, and that's why we are expected to write down the boundary conditions and use them as in the process of solution, finding out the solution. So let us have some more idea about this. To determine the temperature distribution in the medium and the rate of heat transfer, it is necessary to solve the appropriate form of the heat equation. Already I explained you in the last slide. However, such solution depends upon the physical conditions existing at the boundaries. As I told you, multiple solutions may be possible, but for specific set of conditions, we may get a specific solution, and those conditions, specific set of conditions, at the space along with the space. If you are referring or if you are specifying them, then they are called as boundary condition of the medium. And if the situation is time dependent, means if time is involved, then we need to specify the condition based on the time, and that condition is called as initial condition. So if you go refer to the equation of generalized conduction equation for Cartesian coordinate or spherical coordinates or cylindrical coordinate system, you find that all these equations are second order partial differential equations. Means each temperature variation or each spatial variation will need at least two boundary conditions, because every time you are going to get two uh, arbitrary constants in the integration equation. So because of heat conduction equations are second order in spatial coordinates, two boundary conditions must be expressed for each coordinate to describe the system, and the equation is first order with respect to time. You can recall del T upon del T, that is the first order equation, and that's why only one initial condition is sufficient for solving the problem. It means if you want to solve this three-dimensional equation, we need minimum six boundary conditions and one initial condition for solving the problem, and that's why it is very complicated to solve analytically. Now we are going to talk about the boundary condition. The first boundary condition is specified temperature boundary condition, which is can be considered the simplest possible boundary condition in all the boundary conditions. Now what is there? Let us consider an object at a location, say at x is equal to 0 and x is equal to L. If we are having the values of temperature with us, we can measure directly the temperature. That is, say at x is equal to 0, temperature is equal to T1, and T1 is measured and it was found to be 150 degrees Celsius. Similarly, the case for x is equal to L, temperature was found is designated as T2 and it was measured and it was found to be 70 degrees Celsius. The temperature of an exposed surface can be usually measured directly and very easily. Therefore, one of the easiest way to specify the thermal conditions of the boundary is in terms of specifying the temperatures, and this is called as Dirichlet condition. When the surface is in contact with the melting solid or boiling liquid, the temperature are going to remain constant, and in such situation, this particular specified boundary condition can be more useful. For example, now how to write down this expression in terms of mathematical formulation. See, consider the case for one-dimensional steady transfer through a plane wall of thickness L, the specified temperature boundary condition can be expressed as C. Temperature at x is equal to 0 is equal to T1, and that is equal to 150 degrees Celsius. Similarly, temperature at x is equal to L is equal to T2, and that is equal to 70 degrees Celsius. Now you can recall the temperature distribution equation. In the temperature distribution equation, T1 was equal to C1x plus C2. So you can put the values of this particular T1 into that equation. You will get one particular equation of in which C1 and C2 are present. Then you can apply this second boundary condition. You will get another equation in which C1 and C2 are present. And you can solve these two equations, two unknown C1 and C2. We can solve them simultaneously, and we can find out the values of C1 and C2, where T1 and T2 are the specified temperature at surface x is equal to 0 and x is equal to L respectively. So this is what is specified boundary condition, specified temperature boundary condition. The next condition is specified heat flux boundary condition. Now heat flux, as you can recall, heat flux is nothing but the rate of heat transfer per unit surface area. Suppose we are aware of a heat flux at a particular location into a system. Suppose this is a system. Once again, I am taking the example of a simple plane wall, and I know what is the heat flux at x is equal to 0. I also know what is the heat flux at x is equal to L. This heat flux maybe say you can say obtained by radiation on this surface, or maybe because of something which is in contact with this particular surface. So heat flux is known to us, let us assume. So many times when it is possible to determine the heat flux on the heat surface, this information can be used as one of the boundary condition. The heat flux in the positive x direction, heat flux in the positive x direction anywhere in the medium, including the boundary, can be expressed by using Fourier's law, because whatever this heat flux is there. Now if you say this heat flux, whatever is obtained at this boundary, it is going to get conducted through this surface. Or in the other line, I can say whatever is the conduction into this, the same amount of heat flux is going to be there on the other side, because we are assuming the steady conditions. So if you assume steady conditions, then these conditions, the heat flux are same. Conduction heat flux is equal to the specified heat flux, and we can express it in terms of this type of Fourier's conduction. So whatever heat flux is there, this known value can be equated with Fourier's law, that is minus k del t upon del x at x is equal to 0 or at x is equal to L, depending upon the value available to us. Then the boundary condition at the boundary is obtained by setting the specified heat flux equal to minus k del T upon del x at that boundary. As I told you already, x is equal to 0 or x is equal to L or anywhere. It's not like that only at 0 and L we can write the things. It depends on the type of problem. The sign of this heat flux is determined by inspection. Now what is that thing? Positive, the direct sign of the heat flux, this heat flux is taken as positive if the heat flux is in the positive direction of the coordinate axis. Means if the heat flux, whatever is specified, is in the positive direction, in this case it is both these heat fluxes are in positive direction. Okay, as they are in positive direction, we are taking a this heat flux as positive, and we are equating it minus k dt by del t by del x. If the heat flux is in opposite direction, means if this heat flux is in the opposite direction, that is in the negative x direction, then this value has to be taken as negative and to be equated with minus k del t upon del x at that respective surface. This is how we can write down the boundary condition in terms of the specified heat flux for the boundaries. Now, this second condition is called as Newman condition and may be realized by boiling or by bonding a thin film electric heater to the surface. So, if you are having a electrical supply and through that electrical supply some heat is supplied to the medium, then in that case, this type of boundary condition may be useful. Now, this specified heat flux boundary conditions is having two specific special cases. One is insulated boundary. Let us try to understand what is the meaning of insulated boundary. Suppose a surface at here it is shown that at x is equal to 0, there is some insulation applied to this surface. Now, what is the meaning of this insulation? Some surfaces are commonly insulated in practice in order to minimize the heat loss or heat gain through them. Means if the insulation is provided, we can assume that the heat obtained or heat loss or heat gain from that side is equal to 0. The heat transfer through the properly insulated surface can be taken as 0 since adequate insulation reduces the heat transfer through the surface to negligible level. It cannot be 0 in real life, but it is going to be very small and can be ignored. So if such type of insulation is available, insulation is provided in the system, we can use that insulation as our boundary condition, and therefore a well insulated surface can be modeled as a surface with specified heat flux is equal to 0. You can recall the previous boundary condition, specified heat flux. Now here when the boundary is insulated, we can say that the specified heat flux is equal to 0, and this 0 is to be equated with Fourier's law of conduction, that is minus K del T upon del X. Then the boundary condition on a perfect insulated surface, that is on the insulated surface, the temperature gradient in the direction normal to the insulated surface is 0, can be expressed in terms of this equation. So what I am doing, minus K del T upon del X, S equal to 0. Why X is equal to 0? Because insulation is there at X is equal to 0. So this temperature gradient at X is equal to 0 is equal to 0. This heat flux is 0, and now the temperature gradient itself will become 0. So we can say that insulated, whenever insulated boundary is there, the temperature gradient can be equated at that location equal to directly equal to the value 0. Second special case, in case of the specified heat flux boundary condition, is called as thermal symmetry. Now, what is this thermal symmetry? Some heat transfer problems possesses thermal symmetry as a result of symmetry, thermal temperature symmetry imposed by the in imposed thermal conditions. For example, two surfaces of a large hot plate of thickness L. This is a hot plate, say of thickness L. It is suspended vertically in air. So on both the sides of the plate, same conditions are there, same temperature air is there. It means that both the sides are subjected to similar thermal conditions, and that is what is called as thermal symmetry. So if such type of thermal symmetry is there, the temperature distribution in half of the plate will be same as the other half, and this is how it is shown. And that is the heat transfer problem in this plate will possess a thermal symmetry about the center of the plane, that is at x is equal to L by 2. So the first whatever is the temperature distribution in this half, the similar temperature distribution is going to be observed in the second half, and at the center we'll get the topmost point. It may be maximum condition or minimum condition, but at the center of this object now we'll get zero slope condition, and this can be specified in terms of the boundary condition. There will not be any heat flow across the center plane because either it is going to be at maximum temperature or minimum temperature. Therefore, the center plane can be viewed as a insulated surface. So this L by 2 surface, whatever is there, can be viewed as an insulated surface, and the thermal condition at the plane of symmetry can be expressed as minus K del T upon del X at X is equal to L by T is equal to 0. Why 0? Because there is no heat flow across the center plane. So heat flux through that center plane is equal to 0. That is what is called as thermal symmetrical boundary condition. The most commonly used boundary condition in practice is this convection boundary condition, because most of the time the objects are subjected to the heat transfer by convection at the outer surfaces. So convection is probably most common boundary condition encountered in practice. In most of the heat transfer surfaces are exposed to the environment, and because of that they are losing the heat by convection. So if such type of condition is there, the convection boundary condition is based on the surface energy balance. So what is the surface energy balance? Once again I am saying, see, you can see that whatever is the heat flux by convection, same heat flux is by conduction. So whatever we have done in the specified heat flux boundary condition, the same logic we can apply here, and we can write down this as conduction at a given surface, conduction at a given surface in selected direction, suppose positive x direction, is equal to convection from the same surface in the same direction, convection from the same surface in the same direction, and both are equal. That is what is called as convection boundary condition. Okay, so at under a convection boundary condition, we can say that the convection heat obtained at any surface is equal to the conduction at the given surface. Same can be written for the another surface. We can write it for the left side of this wall, this side. We can say that at conduction flux can be written by Fourier's law of conduction, that is minus k dt upon dx at x is equal to 0, and that is equal to convection from the surface in the same direction, that is h into T infinity 1. The temperature on this side fluid is say T infinity 1, and heat transfer coefficient on this side is say H1. So H1 into T infinity 1 minus temperature of the surface at x is equal to 0. So this is how we can specify the temperature or the specified condition for the left side. Similarly on the right side, same, that is the rate of conduction, that is minus k dt by dx as x equal to L is equal to the heat transfer coefficient on this side is H2. The temperature of this side is say temperature at x is equal to L minus T infinity 2. Okay, from the directions already we can draw a conclusion that surface temperature in this particular side is going to be higher as compared to fluid temperature. That's why surface temperature is taken as first and the fluid temperature is taken as second. In this side the convection is taking place and then it is followed by conduction. That's why the fluid temperature is higher and the surface temperature is lower. That's the surface fluid temperature is taken as the first temperature and second temperature is taken as the surface temperature. If you remember this, you can write down these equations very easily in terms of the boundary conditions. So this is convective boundary condition. These expressions are equally applicable when the heat transfer is in opposite direction. So doesn't create any difference. If there's conduction and convection both are in opposite direction, then also we can use the same equations for right and left hand side. Only thing which is remember is to be is to be remembered is T infinity 1 is higher or surface temperature is higher. So whichever is higher, the fluid temperature is higher, that has to be taken as first. If the surface temperature is higher, that has to be taken second. So this decision you can take depending upon which mode of heat transfer is taking first, convection or conduction. Similarly, similar to the convective boundary conditions, sometimes it is possible that we can write down the equation in terms of radiations. The equation are very similar to the convective boundary condition, and you can see that the radiation is happening at the surface and the conduction is taking place subsequently. So let us find out. In some cases, such as those encountered in space where convection is not there because of absence of any fluid and cryogenic application, heat transfer surface is surrounded by evacuated space, and thus radiation becomes the only mechanism of heat transfer. Now we can use the energy balance like the previous boundary condition, that is convective boundary condition. We can in the similar fashion we can write conduction at a given surface in the selected direction is always equal to radiation exchange at the surface in the same direction. So we can write down on the left side, okay, the equation for conduction is minus k dt upon dx s is equal to 0 here, and equation for radiation you can recall the Fourier's law of Stefan Boltzmann law of radiation. From that we can write epsilon 1, which is the emissivity of this surface, into sigma into T surrounding raised to power 4. T surrounding is the temperature from which these radiations are coming to the surface minus temperature of the surface at x is equal to 0, and for the right hand side in the same way we can write. Only thing is that here T surrounding is higher, that's why it is taken as first. Here the T surrounding is lesser, it is taken as second temperature. The same convention which was used for the convective boundary condition can be equally applicable to the radiation boundary condition. Now, what is the problem with this radiation boundary condition? That it involves the fourth power of the temperature, and because of that this boundary condition is non-linear, and that's why whatever equations we are getting through these boundary conditions are difficult to solve, and that's why they are resulting into more complications. So most of the time in routine applications, except the space applications or cryogenic applications, we can simply ignore the radiation and we can consider only the convective boundary conditions, or at all if you want to consider radiation into the picture, we can convert the radiation heat transfer for that surface and count it in terms of the convective heat transfer coefficient. So in that situation the heat transfer coefficient will represent both the radiation heat exchange as well as the convective heat exchange, and that is conveniently done in many problems in real life. So this in this lecture we have learned about the what is the meaning of boundary condition, why the boundary conditions are to be specified. We have learned about the temperature boundary conditions, the heat flux boundary conditions, and the special cases associated with the heat flux boundary condition, convective and radiation boundary conditions. And now we already have got information about the generalized conduction equation. We are now aware about the application of the boundary condition. Now we have got ample information available with us, we can use actually for solution of the real life problem. So next lecture onwards we'll be talking about the one dimensional steady state conduction without internal heat generation. Okay, thank you very much.